Rosanne is a senior researcher at Uber AI, which she joined via the geometric intelligence acquisition. A lot of this class has been about like sort of the practical, nuts and bolts of like how do you actually, take these like amazing tools, which are deep neural networks, and make them work on real problems. And so we thought it would be appropriate to wrap up with something of like kind of a different flavor, which is something more fundamental. And a lot of Rosanne's research is on exactly that. It's on like kind of understanding, looking into the black box of neural nets and understanding what's going on. So thanks for being here, and excited to hear you talk.
Yeah, thank you. Thanks. Hi, it's a pleasure to be here, and thanks for the invite. So it turns out I'm the last speaker, not just for today, but for the whole series. I want to first congratulate you guys for having gone so far. Just bear with me for another 45 minutes, or maybe less than that, and you're going to be done with. Not done with being lectured at, not done with learning, and done with projects for sure. So you will notice that I don't have a title yet because I feel like the thing's a little bit different here. So usually when I go out and give a talk, I know what I'm going to talk about. I'm at a conference. I'm going to talk about the paper I published at that conference, and people are at that conference coming to hear about that talk that I'm going to talk about. So what people want and what I can offer are perfectly aligned in that situation. I feel like it's different here because all you guys have very different backgrounds, and some may be interested in kind of becoming an independent researcher like I am, and so my experience will be directly applicable, but some may be interested in, say, building a research lab or trying to hire researchers, so maybe you want to learn from, what I think is a good researcher or research attitude. So all the things are different, so I'm thinking I offer the same thing. I offer my experience, but I wanted to do it in a way that you guys can do different things with the same data. So what I'm saying is, what I'm going to talk about for the next 40 minutes or even less are three things: who I am, to give you a context, and some of the things I've done, so because that's the only thing I can talk about, my experience, and what I learned. So basically, I'm giving you some data. You guys have been working with machine learning problems, so you know what's next, right? With the data, you're going to build a model of me. Each of you guys can build a model differently because you have different brains. And I trust your brain that you can do few-shot learning, one-shot learning, so super fast. I don't have to wait for you to train. And the model is going to be used for yourself to start doing some inference. So you guys are going to ask questions that suit your need, right? I have the same data, but you guys are going to have to ask different questions. So I hope through this mechanism of both me talking and you guys actively thinking what you want out of this talk, we can make a better use of this time. So following this schedule, who I am, really quick, I'm right now a senior research scientist at Uber AI. I've been at the place for 2 years, which I've witnessed it growing from 15% group to right now about 120. So that's when Uber AI started. I was part of the starting team. And we have different divisions in the lab, and one of them is core research, so you just publish. You're like a PhD student there or a postdoc there, and I happen to be in that division, but I also know a little bit of what the other divisions are doing, so you're more interested in, say, how does machine learning apply in Uber products like Uber Eats and the Drive and Ride and everything, or how data science is executed there, how we build a platform so more people from the product team can use machine learning. Then I know a little bit of that, but mostly I'm in core research. So before that, I was a machine learning researcher at Geometric Intelligence, which no longer exists now. If you search for it, there's news that Uber acquired us, so which is good, right? But it's old news, so we don't have a website or anything anymore. I was there for a year. My title was machine learning researcher, but as you know, Josh talked about different roles last time. They can mean different things. Even at a startup, they can really mean just wild things. So it was a startup of less than 10 people when I joined. So we're just basically doing everything: infrastructure, research, writing papers, and everything. Before that, I was a PhD in Northwestern. So some of the things I've done, I was trying to come up with like a simple, concise way of describing it. I think the way to describe it is I work in AI, luckily. So if you think about AI, it's been going on for 5-6 decades. And really, what's really amazing things are happening is the last decade. And really, if you think about it, why it is happening is because neural networks start working out of big compute, big data, whatever factor. but that's the only reason that amazing things are happening these days. And I happen to be having a PhD and developing my first career and second career in that little green zone. So that's the only thing I can talk about. And my work happened to be just following the theme of like staring at this thing, which is neural networks, if you don't recognize it, really hard and try to figure out what I know about it, what I don't know about it, and try to understand it more. So that's like one sentence summary of what I do. I'm going to talk about what I learned, but I'm going to come back to this because it might make more sense when I deeply dive into a couple of practices I do. But just to give you a sneak peek, I think what I learned from doing deep learning projects is that deep learning these days can be both easy and hard. And for me, I think the best way to do it is to try to understand it. Even the things that you think you understand, you might not understand it fully. And I think it's really important to have a researcher's mind. Do you have a question? Oh, okay, sorry. We'll come back to this slide and maybe you understand more, but just to give a sneak peek. So back to what I've done, and that's the main meat of this talk. And hopefully right now I can bring up the title. So the thing I've done is I've been staring at a neural network really hard, coming up with a few insights out of this few attempts of trying to understand them. So I'm going to have 3 parts of the talk indicated by this corner that says part 1, 2, 3. And the first part is this thing that we're looking at, loss. So you guys have been doing projects, you've all trained something, I hope. Can someone tell me what you do when you look at a training and know whether it's good or not, whether it's successful or not?
Loss going down.
Loss going down, cool. Yeah, you look like this one thing, one scalar that's lost. You want to see something like this. It starts somewhere random, goes down. Maybe in the beginning, in the middle, you do something nice. You drop the learning rate, it goes down faster or something. So we look at this and we think it's really odd because the whole network is so big. You have so many parameters, and at the end, you're just looking at one metric. I mean, it's nice to have one metric. You can make decisions really fast, but it's also odd. It also says how little we know about neural network training. We're just looking at this one number. So if you think about what really happens in a single iteration, well, simply one thing happened, the loss moved. But why is it moving? The data didn't change. I mean, if you forget about the mini batch, but just think of the loss as the whole training set loss. Data didn't change. The only thing changing is network weights. So the weights changed, and which is the cause of the loss changing. So really, what we want to see here is how is every parameter's contribution to this loss change. So ideally, we want to have a per parameter loss contribution. We want to associate a number to each parameter in this network. If you have millions, then let it be millions. And ideally, what it means is that if you have k parameters, you would have k loss curves. If you sum them all, you recover the loss curve that you had over here. And you can sum them over different dimensions. Say you can sum them over neurons, over layers, over channels if you're doing a ConvNet. And the math here is actually not that hard. I'm not going to go deep into the math, but if you think about it, it's just each parameter's gradient, which you already have per parameter, times that parameter's movement. So that's the contribution it does on the loss. It's an approximation. It's a Taylor approximation, so it's not super accurate, but you can work out some math to make it more accurate. At the end, we want to make sure that if you sum everything, it is this loss curve. So how do you imagine that many loss curves are like? So the idea is we can visualize it. And the hint is here is not all of them are going down. Some of them are just doing bad things. So I'm going to play a quick video here showing that. So each pixel here is a weight. And you can sum them to make different neurons. And if you see bars going down, that means that weight is helping. You see green is helping. You see purple is hurting. So a lot of weights are hurting the network as the network is training. So this is a training curve. So in the beginning, of course, lots of things are happening. As you're training, lots of things happening, but you can see the amount of purpleness and greenness seems to be consistent. So lots of things are hurting, lots of things are helping at the same time. You can't really come up with a solid conclusion, but this is the way that you can see a big bunch of data really quickly. And then you can make some nice plots to see, to build up. You can have some hypotheses and then come up with plots and measures to see if the hypothesis is true. So, okay. So for this one, say you can try to count. Now you have per parameter per iteration contribution. You can try to count how many of them are hurting and how many of them are helping through training in an iteration. So if I indicate green as helping, red as hurting, so surprisingly, not even half of the parameter here is helping. So almost half of the parameter in the network is hurting the training. So every iteration is making the loss worse. So here you see a bunch of white because it's MNIST, and MNIST, some weights are just never trained because some pixels are just dead, they're never on. So now you know that this number of weights are hurting and helping. You may want to know how much they're hurting versus helping. So that's where a histogram comes in handy. So this histogram is saying it's log scale. So it's really saying that most of the weights are making very, very little contributions, whether they're on the hurting side or the helping side, and only a few weights are doing big contributions, just heavy-tailed. This is kind of like a behavior science analysis on weights. So if you have a population of weights, how are they doing? So you can summarize by layer, so you see how much percentage of each layer is helping. They're all around 50. And you can plot a histogram of per weight. So we know that half of them is helping, half of them is hurting, but do you know, is helping ones always helping, hurting ones always hurting? This histogram says no. Over 50% of the time, one weight is hurting. So this histogram centers around 50%. That means weight jumps around hurting and helping like constantly. So that's MNIST. You can do the exact same thing for CFAR. You see the white band is gone. In CFAR, almost every weight is doing something. But this number is still like hovering around 50%. So that's surprising. A lot, half of the network is doing something bad. And this is a particularly good network. It's ResNet, right? It's supposed to be doing something good, but it's like this number never changes across different networks. It's the same. So almost 50% of the network is hurting, and each parameter hurts 50% of the time. So learning is very heavy-tailed. That's what we found. We ended up finding a lot of additional insights, including some layers actually just hurts all the time, like ResNet. So this one, so in MNIST, everything was fine. This bar going down means is helping. So negative is helping because you helped the loss going down. And in ResNet, it's super weird. The first layer and the last layer always hurts. So that's one thing we found in this section. And then there's another insight that if you plot, so each weight is learning. Now you have each curves of each weight. You can just plot the moments of learning, right? The weights going, like having a big drop. And if you highlight them in red, you'll see that each layer actually learns about the same time. So layer learning is synchronized. If you break that into classes, it's also synchronized. So a lot of insights are developed once we have this measurement that allows you a much richer view of the training process. So that's the first part I want to talk about, looking at the neural network really hard and to understand the training dynamics. Yes?
How do you measure a parameter's contribution?
Yeah, so the method is actually easy. So you already have one thing that's per parameter, that's gradients, right? Once you have a loss, you have a gradient that's already per parameter. And now you have another thing that's per parameter, that is how much that parameter moved, the value that it moved. If you dot product, the gradient, which is the direction, versus how much it moved, that indicates how much it moved the loss. So it's approximation because the loss curve may not be linear, and you might take a too big of a step, and you might have momentums and things that, so your gradient is not exactly your direction, but we come up with math that is approximately pretty accurate. So hope I get time to cover the other parts. So the other part of the talk is about, again, looking at the neural network really hard and try to figure out what happens there. So here we're looking at ConvNets. So ConvNets are so widely used these days, and it's doing amazing things like recognize a dog's breed really easily, like drawing tiny, tiny bounding boxes around human faces, little, really, really accurate object detection, trying to play games right from pixels, and they can even generate images from random noise. So I didn't even update this, so now we have way better results in generative modeling. And one common thing that all this amazing story is that they all use ConvNet. So ConvNet is very successful in all those domains. So if you think about how amazing ConvNet is, that is, it can somehow find this mapping between a vector of random noise, random numbers, and somehow this mapping is found between this one and this amazing picture, you would think that this task shouldn't be that hard. The task here is, if I give you a coordinate index, you paint that pixel for me. You just paint one pixel, not a colorful pixel, not hair, not eyes, not human face. It's just one pixel. And of course, if I move that, that coordinate, you paint another pixel accordingly. So you'd think that this shouldn't be as hard if I am allowed to build as big a ConvNet as possible. But it turns out we found that ConvNet failed at this simple task, and we call this task coordinate transform to be so that we can call it easier. So the task is that if you're given a Cartesian location and you're asked to draw a pixel, ConvNet actually does this really, really badly. And how bad? So we trained a bunch of models. I'm not going to show you that result, but basically we trained hundreds of models. None of them does well. Well, when I say does well, I won at 100% because it's such an easy problem. And if you think about it, it's a classification problem because you're given two numbers, you're given one pixel. So you can really use the best loss that's out there, softmax, cross entropy. It should be good on everything. But it was so bad. The best one was only like 80-some%. And here we're just digging in to see why it is so bad. Because the convolution neural network at the end gives you a softmax probability output over the whole space. And you can really see like why is it doing so bad by both looking at the softmax and looking at the lodges right before the softmax layer. So you can see that it's trying to get to the target location, but never quite. Like sometimes it gets it right, but some probability still leaks outside of this target location. So that's how bad it is. So this is kind of a debugging step to see why it is doing such a bad job. So this direction, we proved that it's hard. We were trying like, what about this direction? What if I give you a picture with one pixel on and I want you to tell me what's the location in Cartesian space? So an easy story here is that it's also very, very hard. It paints pixel kind of, but it's a very sloppy manner. So this is also harder. And then we actually didn't start here. This was the end of a long investigation because in the beginning, we were actually trying to train some generative models to generate some colorful objects moving around. And it was never moving around. So that's why we were trying to debug why is ConvNet doing this thing so badly. And we keep simplifying it and reached this coordinate transform problem. So this itself has already been a debugging process to figure out why it is so hard. So it turns out ConvNet suck at all these tasks when it has to do with coordinates. Yeah.
What's the training data?
For this task is easy. You just generate all these locations. You can have a picture, say 64 by 64. So you would have all these locations, each has one pixel on, and you have accordingly their Cartesian location. So it's a totally supervised task.
And you have a holdout set? Right?
Yeah, I have a holdout set. I didn't do that, but you can have a uniform holdout set when this can be training, this can be testing, or you can have a harder holdout set when you have the whole quadrant, like this one, this lower right corner holdout as test set. So it was bad on both holdouts.
And performed badly on training as well?
So the training was, also bad. You can get trained to be 100%. You can definitely train. You can always train a network to memorize. But yeah, the really thing that we care is the task set. Yeah, I should. Let me see. I still have the slides, but in the interest of time, didn't want to show it. So this will be like all the 200 models that we've trained. So you can definitely train some 100% training. This is train accuracy. So to have a 100% train accuracy is easy, but they overfit, right? So this just means that test accuracy is low. This will be good. We want it to be here. But all the models, they are either very bad or they're getting better, but they start overfitting. And uniform holdout is easier. Quadrant, this holdout, which you hold out the lower, like this corner as test set, which is really bad. So, yep. Yeah, this I don't. So this, we were trying, you're right. So fully connected would solve this easier. But we were trying to figure out a convolution problem because we really, in the beginning, we want to see why it cannot paint things that move. So eventually, we would have to use a convolutional neural network to solve this problem. We were like simplifying it to find this problem, but eventually, we want to make ConvNet better to make things move better. So that was like investigation. When you find a problem is sometimes good enough, you can publish a paper already saying that I have this problem, who can solve it? But lucky for us, we also found a solution. So we called it CoordConv because a convolution works this way, as most of you know. It takes input tensor, outputs an output tensor through some sharing of filters. So CoordConv works very similarly. You just add 2 channels of coordinates to the input tensor, doing nothing, running the same conv, or dconv if you're painting pixels. So it is so simple so that it keeps all the good things that convolution has. So convolution was good for so many reasons. It has few parameters because of the large weight sharing. It runs fast, and it has translation equivariant, which a lot of cases are needed, like image classification. So CoordConv keeps all these good properties. And as to translation equivariance, it can learn to either keep it or forget about it, become translation dependent by assigning weights on these 2 channels or not. So, you wrap it into a layer and it's easy to use. So with any network like this one, AlexNet, you can just swap out any conv into CoordConv, 1 of them, 3 of them, all of them, or none of them, as much as you want. So it's really easy to experiment with your own models. So it turns out to fix this problem really easily. Not only that it generates 100% accuracy on test set all the time, but the logic, even the logic part is like nicely and smoothly laid out. Solved the regression problem perfectly because now it knows the coordinate, it knows where to paint. And so we solved the problem, but then people are suspicious that's only a toy problem. Why do we care about toy problem? In research, we care about real-world problems, or real-world in the research domain, that is all these problems. Like recognizing a dog, I care about. I care about drawing bounding boxes, care about generative models, and maybe reinforcement learning. So because it was so easy to use, everywhere you use conv, we can just swap in CoordConv. So we just tried all those. As expected, it doesn't improve much on image classification because that is where you exactly don't need to know the location of a dog. If a dog is on this corner of an image, that corner of the image is the same, it's a dog. So it doesn't improve image classification, but the good news is it doesn't make it worse. It's the same, so nothing happens there. Object detection is where you really need to know the location, so it actually helps a lot in our little test. So like maybe a tree is always in this corner, it's never on the sky, so it helps you detecting the location and the category of a tree much better when you're drawing bounding boxes with CoordConv. In generative models, it helps with objects moving. It finds a better latent space where the location is encoded. And in reinforcement learning, it helps agents get better scores. So some examples of generative models, like this one, we're trying to just generate objects with different colors. So you can train again with both conv and CoordConv easily. And when you sample, the sample seems fine. They all seem to do the job, 2 objects, 1 red and one blue. But the real difference happens when you try to interpolate them, because that's something you can do in GANs or generative models. So you see that with convolution, there's so many artifacts. Like the pixels just appear and disappear. The objects never smooth. It never learn the object, just learn to paint single pixels. But with CoordConv, things are moving around more smoothly because it now has a better latent representation of the object's location. You can scale it up to paint bigger things. Back then, people care about LSON. I guess now not anymore. But with conv, you can see that things fade in and fade out. Things just appear and disappear. With CoordConv, you see more like moving around. It has learned this geometric transformation. You can use it to play games. So Miss Pac-Man really helps a lot with CoordConv because you probably need to know both where Pac-Man is and what is Pac-Man. Kind of makes sense. So the red is CoordConv makes better. Another game helps it learn faster. Another game, there's no difference. Maybe the location doesn't matter there. So we tried lots of games. Some helped, 6 of them helped, 2 of them were similar, and 1 of them was worse. So the conclusion of this part of the talk, CoordConv, is that we find this curious inability of convolution, and we solved it with CoordConv. It helped solve this toy domain and helped performance boost in a range of other applications. And that was a paper published last year. Cool, I have time to get to part 3. I thought I didn't. So part 3, we are like taking a step back and now looking at training again. So not a specific neural network, but just the training of a neural network. So when you think about how you train a neural network, what you do is actually you have a neural network, you have all the weights, you take all the weights out, and if you imagine a space in front of you of all the weights, a super high dimensional space, what training really is actually starting from somewhere with higher loss and then just traversing the space and end up somewhere, hopefully, with a lower loss. That's all training is. You're moving the weights, each of them, so that the loss is lower. So we're really thinking, do you have to train that way? And what if you make it more restrictive? So we propose this random subspace training where you start the same place. You are still moving the weights, but you're restricted to move the weights in a subspace that is having fewer dimension of the original space. So if the original space is big D and the subspace will be small d, the weights are only allowed to move in this space. And this small space is initialized randomly. You can do it in any way you want. And you still optimize it the same way. Now, instead of optimizing in the original space, you optimize in this space, and then you use a random projection to map it back to the original space, because you need the original space, all the ways to work in your network. And this is initialized randomly and then frozen, never really trained. What we train is this thing. Okay? So in this, you can develop a metric telling you how large must this little d be to solve the problem. So if you think about how well it works, it actually just depends on the dimension small d, subspace dimension. Because on one end, if you have just a dimension of 1, you basically just have one line and trying to find a solution by just following one line. It's very, very rare that you are going to find a solution in this one dimension. But if you're allowed to use a dimension of big D, which is the original dimension, it's almost guaranteed that you will find a solution because you found a solution already with the original network. So there must be a place when this transition happened that a network with some dimension starts to work suddenly. So we can call this dimension the intrinsic dimension of the network plus the problem. Yeah.
What's the reason why would, I guess that this would be the shape, why would it just be linear?
Yeah, it could be linear. We are supposing it's this shape, and I think in experiment it's mostly this shape.
And is there a reason or intuitive reasoning behind that this should be this shape?
No, we don't think it will be linear. In experiments, it's something like this. We think of something like this. There's no perfect reason there. And each problem is different. Yeah, this is just some drawing that we think would be the concept behind it. So bearing this thought, right? So we're just trying to find this line, where the switch happens when network just suddenly starts to work. They have a higher enough dimension. And then we can try it on all kinds of models and all kinds of networks that we have. Say you have an MNIST, people like MNIST these days. And if you have an FFC network that's of this size, say 784, 200, 210. So in this case, this big D is about 200,000. That's how many parameters you have in this network. So guess what subdimension or intrinsic dimension of this problem is? It's actually 750. It's so small that it's only 0.4% of the original space. So with a subdimension of 750, you can already solve this problem pretty well. And what's interesting is 750 is even less than the input space, which makes sense for MNIST because a lot of pixels are just dead, are just always black. And yeah.
So when you say the intrinsic dimension is 750, does it depend on the projection that you are doing?
It does depend on the projection, but if you run it 10 times with 10 projections, it always gives you that number. So we make sure that it's robust. It definitely depends on the projection, but we make sure it's robust against the dimension. Yes.
quick question. What would be an example of a dimension that just to get more practical?
What do you mean?
What would be an example of a dimension, for example?
So you can think of a dimension as all the search space in your network. So the network have 200,000 parameters. That's like all the things you can move, all the control variables or degrees of freedom as you may. And this number we find is if we restrict it to search only in the small dimension, so you have a...
You can only move 750, update 750 neurons in the whole network?
No, you're only allowed to move in a direction that's of 750 dimensions. It's harder to think in a high dimensional space, but if you think in a three-dimensional space, you have a 3D world, but I restrict you to only move in a 2D plane. You can only move here and try to search for a solution.
So how would
That's
you
probably
actually,
easier to think.
How would you actually impose that restriction?
So you have a small vector that's 750. You just search it here. Whenever you have a solution, you map it back to the big one through a random matrix. And that one will become your weight matrix. You run the forward the same way. You run the backward, and this has gradient through this matrix, and this small thing would have gradient. So you update the small thing only. That makes sense?
So you are imposing linear constraints between
Yeah.
the...
Okay. It's a linear projection. Okay. True. So you have 750 for MNIST plus FC network for this particular FC network. And interesting, if you make it slightly wider, like 225 instead of 200, number is still 750. So this number drops a little bit, but it's still 750. If you make it much wider and much deeper, try a lot of things, and this number is still 750. So what this tells you is that this measure, intrinsic dimension, is fairly stable for this problem with this family of model, the FC model. And something else it tells you is that people know that with deeper, larger neural networks, it's easier to train, and maybe this explains why. Because the intrinsic dimension is the same, so when you make the network bigger, you're basically just having more solution space. Because the solution space, if you think about it, is the original space minus the dimension that you can search. Yeah.
Have you tried combining this with the first goal to describe, like, the intrinsic dimension of the problem as anything to the negative contributing?
Yeah, it could be. This work is much earlier, or a year earlier, but that work is new. But yeah, that's a good point. You can see that whether a network is more or less intrinsic dimension would have less parameters hurting. That could definitely be a valid direction. So, but this is just a small network. Let's just try more, because we can try more. Wait. Okay, so we know that MNIST plus FC is 750. What about a ConvNet? Okay, cool. What about ConvNet? I revealed the answer too soon, but it's lower because ConvNet is a better network to solve this problem. So a lower number would be, it's easier to search for an answer in this network. So that just suggests that ConvNet in this situation is a better network for MNIST. What if we shuffle pixels? People sometimes do this to study generalization and overfitting. If you shuffle the pixels, it doesn't change for FC network because the order doesn't matter for the FC network. So it's still 750. But if you run the same ConvNet, guess what? It's much, much larger. So ConvNet is a better model when your input data has structure, spatial structure. When you break the spatial structure, ConvNet is a much, much worse model. I guess people already know that, but this number just vividly tells you that and how much worse it will be. So this sheer difference tells you that. But enough of MNIST, people care about larger problems, right? So we measure CFAR. CFAR with an FC is about 9,000. CFAR with a ConvNet is about 2.9 thousand. So that's interesting when you compare this 290 versus 2.9K. So now you can tell people that CFAR is harder than MNIST, but how much harder? Maybe 10 times harder. It's like a number that you can directly use. You can do ImageNet. It's much harder to scale, so we use a SqueezeNet, and that at that time before the conference deadline, we didn't really fully train it, but we know it's a number that's larger than 500K for this network, at least. And one particular interesting thing to do is you can use it anywhere that you use a network. So you can really use it on RL, and you can come up with numbers now that you can compare with supervised learning, which is never done before. So now you can really say that, well, having a humanoid to walk in RL is about the same difficulty as training FC on an MNIST, which people can never make the analogy before this tool. And playing a pawn is like about as hard as training a CFAR10 on an FC network, something like that. It's like roughly, but of course now you can say that. And know that this problem has only 4, so this is a super easy problem. Like before, if you ask which problem is easy or hard in RL versus supervised learning, you have to have someone that work in both fields and have played with them really heavily to tell you that. And people usually work on one field or another. Rarely you see people working on both fields to really make this comparison. So they may have this comparison in the back of their head, but it's very hard to really say that. But now you can say, they're this much comparable, and this problem is actually super easy when you play with RL. So yeah, interesting. I have some free time. Cool. So yeah, questions?
Did that change when we changed the random initialization?
Yeah, no. So that we make sure that, well, you change a little bit, but it must be within some bound. So every number there is tried with at least 10, 20 times, and every time the random projection is different. It's a random seed. So to summarize what I've done,
Is there a tool to find out the intrinsic dimension for a problem?
I'm sorry?
Is there a tool or method to find out the intrinsic dimension for, let's say, these networks? Like say, any network that we come up with, can we find out?
Yeah. Yeah, so here you can just use this tool to find out. It's a little bit expensive because really you need to try like all these dimensions until you find the switching point that network starts working, right? There's not a direct way to find out it yet because there's like some investigation we've done. But yeah, not like a direct way you can just measure it once. This like you have to train lots of them. But this paper is more of a proof that there exists such a thing. So that summarizes my piece of work of like staring at something really hard, and of course have to thank my collaborators. Every work, as Peter mentioned, is a teamwork. In research, nothing is like one person group cannot do much. And for the published work, we have written blog posts and filmed videos, which does a better job than me presenting here. And this one is still in submission. It's pretty new. So back to the slides I showed before, I think what I learned here is that deep learning can be both easy and hard, because some of you might have that intuition already. Like people on one side of the story, people are claiming deep learning is doing these amazing things, solving goals, solving StarCraft and everything. And on the other side, when you try to apply it to some real world problem, it's just like really hard to get it working somehow. If it's not an exact image snap problem, it's just really hard to work. Although there are so many tools out there, so many papers published every day, it's just still really hard to manage. So I feel like this is true. So the first sentence just saying that it's definitely true. And for me, I think it's just because people lack a really good understanding of a lot of things, even things that are working. Like even for 2 of the projects, things are just working there, right? Things are just training. But we're trying to understand why, even it's working, can we understand more of why it is working or where it is working? And for the things that don't work, of course, we want to understand why it's not working. I feel like a lot of things that are not happening in industries that people might be lacking a researcher's mind. That is, things that work, we just quickly deliver it. Things that don't work, we quickly abandon it. But maybe like, I know people there have less of a luxury than, really in a researcher lab, you're allowed the luxury to study a problem with more time and more resource. But I'm just saying that I think that might be the little solution there, that people just have to be treating problems, whether they're working or not working, with more patience. And that might be, a good recipe for you guys to take home. Cool, and that ends my talk. And if you have time for questions, do we? Yeah.
How do you see the intrinsic dimension thing relating to lottery ticket analysis?
Yeah, definitely. There's definitely some linkage there. Something small maybe is harder with a small intrinsic dimension, it might be easier to find lottery tickets. There might be more lottery tickets around. There still lacks a way to find how many lottery tickets are there in a network. So that paper says lottery tickets exists, but if you can like count that number, I believe that number has to do with intrinsic dimension in a reverse way though. Smaller intrinsic dimension, more lottery tickets, kind of what I believe.
Yeah.
Yeah, so you're comparing two complexities, 290 versus 2.9K.
Mm-hmm.
Do you think it is like, I guess linear, or is it like, you can compare it that way, or is it?
I don't know. It's a rough measure that's people never studied before. I think it's just fun to say it this way. It's not super scientifically sound, but when you say some problem is harder, how many times harder, it's like already a vague thing that you're putting out there. It's never really scientifically sound to start with. But yeah, that's something you can do with this.
It's a visual notation of machine learning.
It's a good way?
It's a visual notation of machine learning.
Yeah, true. Okay.
So if you have a bunch of parameters in your network that are actually making the loss function worse, then like kind of, and obviously the try would be like, maybe we should do something about this. Like
Yeah.
maybe we should set the weights to 0, or we should adjust the learning rate or something.
Yeah, so we did something like that. And interestingly, I think it's like the same thing with behavioral science with people. Like if you fire the people that are bad behaviors, some people just slowly shift to be bad behaviors or something. So we found the same thing. If you like freeze the layer that are hurting, like some other layers just start to hurt. I feel like this is an interesting analogy to be made here. So like, is a group behavior, and somehow if you kill all the bad actors, some actors just become bad actors.
I have like a more basic question, maybe that's more thing. Like, so when you say that it's hurting, you're saying that it's making the loss function worse, right?
It's making the loss go up.
Yeah. So is that just an artifact of a fancier gradient descent algorithm? Like if you just did the most basic thing and moved in the direction of the gradient, wouldn't only the loss go down?
Yeah, it is true for that mini batch. But the loss that I'm talking about is measured the whole training set. So if you use only gradient, not fancy thing, and you use the full batch of the whole set, and that will be true. But people don't do that because that's not even effective.
Yeah, related to the past two questions, when you say that half of the layers or whatever percentage are doing bad, are they consistently the same weights that are doing bad throughout the training, or do they?
Yeah, no. So that number is consistent. 50% are doing bad, and then another number is consistent. That is per weight, 50% of the time it is doing bad. So that means that they just like switches. Yeah.
So even if you zero them out at the times where they're good, you won't use them, so it would be bad.
Yeah, but one thing we found is consistent. That is layer-wise. At least for ResNet, the last layer just always a bad actor. It's always hurting. So the last layer, the last FC layer, basically, right after the global pooling. So maybe it's too big, and it's like FC just always weird in a ConfNet. The last FC is also always weird. So that one, because it's so consistent, all the weights in that layer just always hurting. If you freeze that one, it helps a little bit. Yeah. How many questions are we allowed to take?
Yeah, time for, let's say, 2 more.
Okay. Maybe I get to pick.
Does the dimension complexity like MNIST or CFR being 10 times harder than MNIST to correlate with compute time for those?
That's a good question. Maybe. Yeah, maybe. But it's hard to compare this way because CFR is also there's more input channels. It's a harder problem. I think
it's a mix of the problem.
Yeah.
What the problem is and how complex your network is.
Yeah, it's like almost always a harder problem. We indicate that you need more data, you need more compute. So it's not directly compute, but it has also to do with the data. In CFR, MNIST, CFR has like about the same level of MNIST data, but it's a much harder problem. So we would say that I would agree that it's more compute, so probably slower. It was the same network though.
Does the dimension change if you double the data?
That we didn't try. Yeah, I think it would make things easier. It's basically a measure of how hard the problem plus this current network you're using is. If you make a network more powerful, the dimension would change. Yeah. Yeah, we just like try different numbers, and you see some switch here, and then you do more like granular search within that two numbers. Yes, it's just mostly for scientific purpose, not super practical here. It's just basically proves that this thing exists. And once you found it, you can make use of it like for model compression and everything. But this paper was basically saying that this thing exists.
Yeah, I'm still a little bit confused about how you measured a neuron is hurting, the overall loss versus not. So, you'd change, like freeze all the other weights, change only that weight and in some direction, and see if that hurts the mid-batch loss or.
Yeah. So basically, when you train everything moves, right? And everything moves a little bit towards the direction of their indicated direction, mostly indicated by the gradient, but with some fancy other terms. So you're moving towards that direction. That's the direction you're moving. And then the amount of how much you're moving is the amount. So like if you're on a weight space, you move this much along this direction. So this direction times the amount will be the drop of loss. If you think about loss as like a surface, you move along the surface this much, right? Going down this way. The loss is actually this bit. Yeah.
But the neurons, like if it's much layered, then it has more like a cascaded effect, right? If you change update one neuron weight, it doesn't mean that you can directly map it to the overall final end loss. It might have some unseen, understood impact along the way there, right? Even though you have the background, which is just an estimation.
Well, gradient already is calculated based on all these dependencies, but once you have each per weight gradient, you almost can neglect the dependency, because now you just have your own direction to move, and how much you moved depends on something else, and that's like exact how much loss you are impacting, how much you're impacting the loss.
The gradient for each. Okay, got it.
Yeah,
Right.
yeah.
All right.
Cool.
Unfortunately, that's all the time we have. Let's thank Rosanne
Okay.
again.
Thank you.